Okay, quick review. So I picked a couple kind of key representative problems from all of the problem sets that are up in Chapter 7. This will be the last test for the year. Will be Chapter 7. It's pretty important stuff, but it's not as hard as 5 or 6. You'll see that. It's a good opportunity for a lot of you to really bring up your grade, though, I think, because this is a test that I anticipate everybody will do pretty well on. This could bring things up. Okay, so what about this? So we want to, this first example, this first page here, we're looking at rewriting expressions. So the first one, I want you to rewrite that radical as a rational exponent. Remember, rational exponent just means fractional exponent. Ratio means fraction. So what would that become if I write that with an exponent instead of radical? Yeah. 15 to the 1/4. Whatever the index of the radical is, that always goes on the bottom of the fraction, right? That's our exponent way of saying a radical or a root, is by having a denominator in the exponent, okay? What about the second one then? What if I want to do,
26.
yeah, if I want to take the 15th root of 26 to the 8th power, well, that's really just two parts to that, right? I've got a 15th root, which we do with a 1/15th power, and then to the 8th power means I'm just going to multiply that by 8, so I get 8/15ths. Long story short, you know that the index always goes in the denominator, the normal exponent goes in the numerator, right? So this one just looks like 26 to the 8/15ths. Okay? So let's reverse it. How would I write this rational exponent as a radical?
7th root of 10 to
Okay.
the 12th power.
7th root of 10 to the 12th power. Okay? I could also write that if I wanted to. I don't think you're going to like this option as much, but I could also write this as the 7th root of 10 to the 12th. But 10 to the 12th is a pretty big number. We'd have to write that number out, so it would look like this. The 7th root of okay, that's 10 to the 12th. 1 followed by 12 zeros. Probably the top way is more convenient. Okay? Make sense? Okay? Okay, evaluate the expression. Now you got to be a little bit careful with these. So if we want to evaluate this expression, we have to do this in two parts, right? So what's the first thing we do? Okay, yeah, we do the radical part first. So Braxton,
There's no answer.
there's no answer. How come?
Because you can't have a negative number out of a positive root.
Under an even root, right? Good. You can't take an even root of a negative number. And because the 4 is even, and this is a negative number, we know that the answer is n. Right? We can't take an even root of a negative number. Never have been able to, never will be. Odd roots, it's just fine. Only even roots that we can't do that, right?
What if the odd root was like 34 and even one was like half?
That'd be fine. Okay, so for example, good question. So what if you had the cube root of negative 8 to the 4th? No problem. What's the cube root of negative 8? Negative 2. So that would just equal negative 2 to the 4th, which is what? Positive 16. Okay? So that would work. That'd be fine. Okay? Okay, what about one of these? How about, what if we want to do, what about that? What's that mean? So what is it? What's that mean? Now, when we do, you guys can do this in your head. When we do a fractional exponent like this, we always start with the bottom, which corresponds to the root. Okay, so what are we doing first then? And you don't have to write this out, but this is how you're thinking about it. You're thinking about this as what kind of root of 16? Fourth. Because of the 4, right? To the third. You don't have to write it out. You can do it in your head. What is the 4th root of 16? 2 cubed 8. Right? Okay. Start with the bottom, then do the top. Okay. Okay, what about something like that? Yeah, what do you do with these? Now, they look scary because they've got fractions in the exponents, but they're not. Fractions are just numbers, and they follow the same rules of exponents we've always used, right? So, yeah, so what's bigger here? Now, remember what our rule is for dividing like bases. And would you agree we have like bases? What's the base? 11. Okay, well, they both of these powers have base 11. So like bases, when we divide like bases, what do we do? What do you do if you divide like bases? What do you do to the exponents? Subtract. And we always said that we want to keep the bases where they have the most power. So what's bigger, 3/5 power or 2/5 power? 3/5, right? So we're going to keep it on the top. Keep the 11 on the top. And we get 11 to the 3/5 minus 2/5. So what is that? Yeah, 11 to the 1/5. Done. Okay. Now, this can get a little bit trickier if the bottom is a bigger power. So let's look at one of those. So what if we have instead, what if we have something like this? What if we have, girls, shh. Right. What if we have 7, whoops. 7 to the 1/3 divided by 7 to the 3/4. Like bases, agreed? Okay, bottom is a bigger power this time, so we keep the base on the bottom and subtract the other exponent, right? So we end up with 1/7 to the 3/4 minus 1/3. Now you guys can do this in your head. These are not hard fractions to combine. We have to get a common denominator, don't we? So what's my common denominator going to be? 12. So I have to multiply the first one by 3 and the second one by 4. So I'm going to get 9 on the top, right? When I multiply by 3, I'm going to get 9 in the first case and 9 minus 4 on the top over my common denominator of 12. Agreed? So this equals 1/7 to the 9 minus 4 over 12, which is what? 7 to the 5/12. Okay, that's the right answer, but it's not simplified. I can't have a radical on the bottom. I got to get rid of that fractional exponent. So remember what we do here. We got to get a regular, what are we going to do? Not the reciprocal. We need to get the bottom, we need to get that 7. We're stuck with a 7 on the bottom, but we want to get the 7 on the bottom to an integer power, not a fractional power. So we have to boost it up to the next available option. Well, what's the next integer after 5/12? 12/12, or 1, right? So we need to multiply the bottom. We need to multiply the bottom by 7 to just the right power to get 7 to the 1. If I multiply like bases, what do I do with the exponents? Add them. So what would I add to 5/12 to get 1? 7/12. I need to get 12/12, which is 1. So we're going to multiply the bottom by 7/12. I got to treat the top the same. So I'm going to multiply by 7 to the 7/12. And I end up then with, on the top, 7 to the 7/12 divided by 7 to the 1, which is just 7. So that's my answer. Okay? Okay? Make sense? Okay, what about this? Now this looks pretty ugly. When you write things in terms of radicals, they always look worse, and they are harder to deal with. So what do we probably want to do with this?
You can, like,
Make those fractional exponents, right? Rewrite those with fractional exponents. Get rid of the radicals. So what are we going to end up with on the top then? Yeah, right, I get 7 to the 5/7 divided by 7 to the 19/7. Okay, so I subtract, divide like bases, we subtract. Bottom is a bigger power, so we keep it on the bottom. And we get 1 over our base on the bottom to the 19/7 minus 5/7, which is what? 14/7, which is what? 2. Right? I just end up with 1 over 7 to the 14/7, which is 1 over 7 squared. Am I done?
49.
Yeah, 7 squared is a number, that's 49. Okay. Good. All right, so what else? Okay, something like this. Now, think about what you can do. We could write these in terms of fractional exponents. I'd say you don't even have to here. Think what we can do. Think back to what we've done in the past when we had things like, let's say we wanted to simplify a square root. Let's say we wanted to simplify, for example, the square root of 50. Well, what did we do? We broke 50 up into the product of a perfect square and whatever else was left over, right? So we wrote it as what? Square root of 25 times the square root of 2. So in other words, we can split up a radical into the product of two numbers, or we could do the opposite and we could combine, if they're the same kind of radical, we could combine the product inside one radical, right? So these are both cube roots, aren't they? So I could contract those or condense those into a cube root of what number? What could I do? If I reverse the process of splitting them up, I could have started here and gone there. So it's going to be what? 125. It's going to be the cube root of 5 times 25 under 1. Because it's the same kind of radical, I can squash them together, condense them into 1, and I get cube root of 125, which is what? I think I heard it. 5. Okay. Okay, what about that? Now notice here, same kind of thing. Are those like bases? No, they're not. They're not like bases, so this is a different kind of problem than we had, for example, right there, right? Here I had like bases, and so I could just subtract exponents. This time I don't have like bases, but what do I have that's the same? The exponents. If I have like exponents, that's just as good. I'll show you why. Maybe you'll show me why. Remember this rule. If I have A over B to the M, what's that equivalent to? What can I do with the exponent there? I can distribute it, can't I? So I could distribute the M to both the top and the bottom, but I can also go back that direction. If I started here, I could go there, right? So if I have the same exponent in both the top and the bottom, I could factor it out, right? Like I have here. I have the same exponent there and there, so why not write that as a quotient to the 2/7? Well, what goes on top? 27. 9 on the bottom, so I'm just undistributing the 2/7 power from both parts. Why is that helpful? Okay, good. I can reduce the fraction, right? I can simplify. 27 over 9 is what? 3. So the answer then, I can write this just as 3 to the 2/7. Okay, now we're done. Simplify. Make sense? I could have also, maybe some people saw there's some other ways to do this. I could have also written the 9 as a 3 squared and the 27 as a 3 cubed and gotten like bases, but there's really no need here. Okay, what about this? Looks terrible, but it's not. Simple rules. What do I do if do I have like bases there?
Yeah.
Okay, what are my like bases? The bases. U and Z, right? So when I multiply like bases, what do I do with the exponents? Add them. That's it, right? So we get, what about the 10 and the 2? If I'm doing a product here, what number do I end up with? 20, sure. Multiply the numbers first, and we get 20. Now, what about the u's? If I multiply u to the 1/4 times u to the 1/4, that gives me u to the what? Yeah, 1/4 plus 1/4. Everybody agree that's 1/2?
Yeah.
If I get u to the 1/2, that's an easy one to do in our head. What about, though, the z's are a little more complicated. I end up with z to the 2/5 plus 3/7. So what's our common denominator going to be? 35. So we multiply the first fraction, top and bottom, by 7 to get 35 on the bottom. Other fraction by 5.
What would be 29 and 35?
And does everybody see why? Because we're going to get, if I multiply by 7, that's going to give me 14 on the top here. Multiply by 5, I'm going to get 15 on the top here. 14 plus 15 is 29. So I end up with this being, this is just going to be z to the 29 over my common denominator, 35. Right? So my final answer then just looks like 20 u to the 1/2 z to the 29 35. Okay? Not so bad, is it? Really, this isn't so bad. These fractions, once you get used to adding and subtracting them a couple times, and you kind of get over the hump of remembering how to do that, it's not such a big deal. Okay, this one, I'm going to put this one off for just a second because if we have time, we'll come back to it. But we've already done some stuff like this. When I divide like bases, I subtract exponents, right? Okay? Okay, this is a good one to review, though. This is my great trick. Remember the trick I showed you? This is the one, you can do this in one step if you just think about this the right way. You don't have to show any work, you can just write the answer down. When we simplify a radical like this, remember that our result is just going to look like some outside stuff times the stuff that's trapped inside the radical that doesn't make it out, right? And the way we do this with variables especially, it makes it easy. All we have to do is think about the power of the variable that's represented. Write it as a mixed number. The integer part of the mixed number comes outside the radical. The fraction part is what's stuck inside. Okay, so let's take these one at a time. What's my total power of x there? What's the power of x inside the radical? 1. What does this do, though? It divides it by 4, right? I'm distributing a 1/4 all the way through. A 4th root is a 1/4 power, isn't it? So would everybody agree that the total power of x there is x to the 1/4? So if I rewrite x to the 1/4 as a mixed number, it's just a fraction, right? It's not even a mixed number, it's just x to the 1/4. So in other words, no part of the x makes it out of the radical. What we're left with is just plain old x to the 1/4, right? Okay, what about the y's? That's a little more exciting, what happens with the y's here. We get y to what total power? 7/4. So that's equal to y to what mixed number power? If I want to write 7/4 as a mixed number, it's what? 1 3/4. So I get y to the 1 3/4. Well, the 1 goes outside, so I end up with y to the 1 3/4. See? Right? What about the z? I get z to what power? 16/4, which as a mixed number is what? It's just an integer, it's just 4. So what's that tell you about the z?
It goes-
It all goes outside to the fourth power. So that's my answer. I just get y, I don't need to have the 1 there, y times z to the fourth times the fourth root of x times y cubed. And story. Okay. All right, top one.
Yeah.
Good luck.
Thank you. Bye.
See ya. Okay, on to graphs. This ought to be pretty fresh in your mind. We just did this stuff. So what I want you to do with these, I want you to write the function down, and then I want the domain and the range. So we're just going to fill in the blanks. We're going to write down f of x equals what? Okay, so what about that? Is this a square root or a cube root? Which one?
Or square.
Square. How come you know square? Okay, because it only goes one direction. It starts at a place and goes only in one direction, right? So what are the values then of h and k? Which of those points is hk? Okay, the starting point. So this is hk. So what are the coordinates at that point? -3 to -1. Okay, what about a? What's the value of a and y? +3. How come? Okay, good. If I go to the right by 1, I go up by 3. So a is 3, right? So what's the function then? What is this one equal to?
+3 minus.
Good. A times the square root of x minus -3. So x plus 3 plus -1. So just -1. Good. That makes sense? Okay, now the domain and the range. Remember, d before r, x before y. Domain is the set of x values that are graphed. So what is that set? If I want to write the domain down, what is it? X is greater than or equal to, good. To what number? Say it again. -3, exactly. Now why? Okay, think about why. Because when I'm drawing this graph, here's a great way to visualize this. When I'm drawing the graph, I put my pen down at -3, and as I draw this graph, my pen is always moving to the right, isn't it? It's going up, sure, but in terms of horizontally, it's going to the right, not the left. Agreed? So the x values, which are the horizontal values, start at -3 and get bigger. How do we say that using an inequality? X is greater than or equal to, meaning starting there and to the right. Greater than or equal to -3, right? What about the range? Yeah, here, same kind of deal, right? Y is greater than or equal to -1. How come? Because the y values start at -1, right? That's what that value is, -1. And as I draw the curve, draw the radical function, my pen is always going up vertically. Yeah, it's going to the right horizontally, but vertically it's always going up, not down. That's why we have to choose greater than or equal to. Now, what if this function had opened up downward? Would have been less than or equal to whatever k is, -1, right? Okay? Okay, what about this one? Square root or cube root? Cube root. So real quick, we'll get it out of the way. What are the domain and range of this? All reals. Yeah, everything, right? There are no restrictions. I don't start any place this time. It goes forever to the left and the right and up and down. If I extended it out off the screen, it would never stop, right? Okay, so let's write what the function is then. Which of those 3 points is hk? Middle one. Okay, so then hk equals, what is that? -5, +3, okay. And what's a? A is 1, once again, because when we go to the right by 1, we're going up 1. So that tells us what a is. So then this function must be y equals 1, which I don't write, times what kind of radical? Cube root. Right? X minus -5, so +5, +3. Okay, that's it. No big so. Okay, last issue of maybe the year. Solving radical equations. Okay. So this is just another example of trying to isolate x, at least in this case. So what are we going to do there to isolate x, do you think? What makes sense? How am I going to get that x by itself?
Square root.
Not square root.
I mean,
Square. Yeah, okay, doesn't that make sense? If I want to undo a square root, don't I just square both sides? Right? Okay, so if I square both sides, I get an answer of 9. Okay, but there's a really important thing you got to remember here, and it's easy to forget this, so don't pay attention to this, 'cause this is important. Whenever you do this, whenever I take both sides to a power like that, that means that I might introduce what are called extraneous solutions. Extraneous mean extra irrelevant solutions. So they're solutions that seem to work, but they don't. Okay, so what the moral of the story is, when you ever take both sides of an equation to some integer power like that, if I square both sides, or cube both sides, or take both sides to the fourth, etc., I always have to go back and check my answers in one of the steps before I did that. So I have to go back prior to this step, which means right there, and see if it works. Well, it doesn't. If I put 9 in for x, is it true? It does work, doesn't it? So this is a legitimate solution. Okay, x equals 9, but we have to check every time. Okay? All right, let's look at another one. What about this guy? What am I going to do? What am I going to do here? Got to solve for y, so I have to isolate y. Subtract 5. Okay, good. Now what? Either multiply or divide by -1. Good. Now what, Braxton? What are we going to do?
Like 5 to the 4th power.
Okay, I'm going to take both sides to the 4th power, aren't I? Now let's for a second here, let's think about why we're doing that. Why are we taking both sides to the 4th power? One way to think about it is a 4th power undoes a 4th root. You can also think about it in terms of the exponents. Just real quick, if we look at this, how can I rewrite the 4th root of y as an exponent? What is that? Y to the 1/4. So if I get y to the 1/4 equals 5, what power could I take both sides to get rid of that 1/4 power? The 4th. You see why? If I take both sides to the 4th power, look what I'm doing. When I take an exponent to an exponent, what do I do? Power to a power, I what the exponents? Multiply. And if I multiply reciprocal fractions like that, 1/4 times 4, what do I get? 1. Yeah, so multiplying the 1/4 by the 4 just gives me a y to the 1, or just a y on one side. On the other side, I get whatever 5 to the 4th is, 625. Okay? So, that make sense? We got to check it, though. If we go back, now where do we have to go to check it? I can go any place above this step right there, right? That's the step where I took both sides to a power. So I could take my pick of either there, or there, or there, whichever's most convenient. Probably right there, how about it, huh? Okay. Does it work? Is the 4th root of y equal to 5? Yeah, it is. Okay, so it checks. It does work. You might be wondering, when does it not work? Well, you'll see. Okay, how about the one on the left? 3x to the 4/3 equals 243. What's the first step to isolate x there? Yeah, I got a reverse PEMDAS. The first thing is I'm going to divide by 3. Okay, now what? Now what do you suppose I do here? Think about the last example I showed you. How are you going to undo x to the 4/3? Take both sides to the 3/4, right? Does that make sense? If I take both sides to a reciprocal power, x to the 4/3 times 3/4 would cancel, right? So there's our trick, or there's our step. Now we gotta be careful with this though. On the left side, I'm gonna get just plain old x, right? On the right side though, think what this means. 81 to the 3/4. Remember what I said earlier? I said you always do the bottom first. So first we're gonna do the 4th root of 81, and then we're gonna cube that. Okay, so what's that gonna give me? If I just ignore that 3 for a second, if I take the 4th root of both sides to isolate x, what am I gonna get? 3, yeah, or what? Remember the rule, if I take both sides of an equation, if I take an even root of both sides of an equation, what do I have to include?
Oh.
Plus or minus, right? Does that make sense? That's a little tricky, isn't it? But taking a 4th root, if the 4 is on the bottom, right, what this really means is, either way you slice it, it's an even root. If I take an even root of both sides of an equation, I have to do the plus or minus, just like we did with square roots. So I get the answers plus or minus 3 cubed. I have to try them both. Okay, so what do I get? What is positive 3 cubed? Positive 27. What is negative 3 cubed? Negative 27. So I get two different answers, plus or minus 27. Where do I go to check that? Where do I go to check it? Above which step? Above the, well, I could do the second, I have to go above, that's where I take both sides to a power, right? So I gotta go above the 3rd step. So either of the first two, I'd say probably the second one. It's a little easier, right? So if we plug in 27, does it work? Positive 27, what's the cube root of 27? 3 to the 4th? 81. What if I plug in negative 27? What's the cube root of negative 27? Negative 3 to the positive 4? 81, sure. A negative number to an even power is always positive, isn't it? So those both actually work. Okay, what about this guy over here? Now let's look at this one. I'm going to make a little switcheroo on this one, though. I'm going to make that a negative 6. Okay? So we're going to do this with a negative 6. All right, so what do I do first? Add 4. So that's going to give me the square root of 2x plus 8 equals negative 2. Okay, now what? Now what? Square both sides. Right, because I'm going to undo the radical, right? Okay, so if I square both sides, I'm changing colors. Why? You don't always have this luxury when you're doing this on paper, but whenever I do problems like this on the board, I always change colors. Why do I change colors here? Because I took both sides to a power. So that's the step where I might be introducing extraneous solutions, right? Okay, so what do I get on the left side? 2x plus 8. What do I get on the right side? 4. Negative 2 squared is 4. From here on out, it's pretty simple, right? Now what do I do? Subtract 8. Divide by 2, right? So I get the answer x equals negative 2. Where do I go to check it? I got to go to the yellow zone, right? One of the two steps before I turn blue, right? Doesn't sound good. So I'm still breathing, trust me. So what about if I plug negative 2 in? How about right here? This would be a convenient one to check. Okay. So if I plug in negative 2, I'm going to get, what's 2 times negative 2? Plus 8? 4. So I get the square root of 4 equals negative 2. Is that true? That is false. So that tells me, what about this solution? It's extraneous. It's a false solution. We have to discard it. And so what would my answer be on Moodle to this one? N. There are no real solutions, right? Okay? Okay, so now the example, I'll put this PowerPoint up. On the example in the PowerPoint, it was a positive 6, and so it actually works. Okay, but I wanted to do one that didn't work. Okay, what about these? Now think what we've been doing in all these prior examples. We've been able to isolate x by just simply reversing order of operations. This is a little bit trickier, isn't it? On this one over here, I have two x's inside different radicals, so I can't combine them. But I can do the same kind of trick. Can anybody think of a way out of this predicament here? What could I do, do you think?
Move the x's opposite sides.
I could move the radicals to opposite sides, because if I can simultaneously isolate the radicals, now what can I do? Really, the problem here is that those x's are inside the radicals. If they weren't inside the radicals, I could just solve this like a normal equation, right? So is there a way I can get rid of both of those radicals? I can square the whole thing, right? Square both sides. If I square both sides, what am I going to get on the left? 12 minus 2x. Now, what am I going to get on the right? Say it again. 4 times x, right? Does everybody see that? Because I have to distribute the exponent to both the 2 and the radical, okay? So I end up with that. Now it's easy. Right now solving, it's a piece of cake. What do I do? Combine like terms, add 2x to both sides, divide by 6, and I get an answer. And then I have to go back to above which step? Above the third. So I have to look only up there, right? When I check this. So I could plug the 2 in. Let's just say we plug it in right there. I get the square root of 12 minus 4 is the square root of 8 equals 2 times the square root of 2. True or false? True, isn't it? Because the square root of 8 is just the square root of 4, times the square root of 2, which is 2 radical 2, right? So that checks out, okay? How about this side? Over here. Same kind of thing, right? Add the 3 times square root of 2x to the other side. Maybe. Oh, I'm just making dots. Well, you know, make dots here. Okay, so we add this term to the other side, square both sides. So what am I going to get? Well, I guess, what am I going to get on the right side? 4x plus 28 and 9 times 2x, because I got to square the 3 also. 18x, subtract 4x, divide by 14, x equals 2, and if it'll check. If we plug it in, it works. Okay, last one. This is last one. This is it. So what about this one? What am I going to do here? Same kind of problem, isn't it? I've got a square root there. If I could just get rid of that radical, I could solve this normally. So I've got to isolate the radical and do what? It's already isolated. What do I have to do to undo the radical? Square it. Now, if that were a cube root, I would cube it, right? Same idea. So if I square both sides here, though, you got to be careful with this. On the right side, it's really simple. I just get 2x. But what do I get on the left side if I square the quantity x minus 4?
X squared plus 16.
No. More complicated, right? It's not. Remember, and this is a really common thing, a mistake that people make. A plus b squared is not equal to a squared plus b squared, right? It is equal to a plus b times a plus b, which I'd have to FOIL out. Now we have an expansion for that, which you might remember, a squared plus 2ab plus b squared, or you can just FOIL it out too, right? But either way, I get that, right? Let's try to use this expansion. If a is x and b is -4, what does this expand to then? A squared becomes x squared. 2ab becomes 2 times x times -4, so -8x. B squared becomes 16, right? Make sense? Okay, now how would we solve that? That's a quadratic equation, right? I've got x squareds in it and x is the constants. What do I do to solve a quadratic equation? Say it again. I heard it in a couple places, I know I did. What would you do? What would you do? Enid? Okay, but before I can do that, what step do I have?
Oh, you gotta.
Okay, so I gotta subtract 2x from both sides, good. Now I've got a quadratic equation in standard form, it's set equal to 0. So what are my options? One of them is,
Oh, you're with them.
yeah,
Quadratic form.
quadratic formula. That's always an option, but maybe, there might be an easier way, which would be what? Factoring, yeah. Are there magic numbers that multiply to 16 and add to negative 10? Yeah.
8, 2,
Signs?
or negative.
Negative 8, negative 2. Okay, so it does factor into x minus 8 times x minus 2. And then if I use the zero product property, if I set those factors equal to 0, what do I get for my solutions? 8 and 2. Okay, but remember, are those both guaranteed to work? No, they're not. I have to check them. So let's check the 8. If I plug 8 in, now watch this. This is where it gets good. You won't miss this part. If I plug the 8 in, I get 8 minus 4, right? Equals the square root of 2 times 8. Does that work? Well, it gives me 4 equals the square root of 16. That's true, right? That checks. Okay, 4 equals 4. Check. Okay, what about the 2? If I plug 2 in, I get 2 minus 4 equals the square root of 2 times 2. Well, 2 minus 4 is negative 2. Does negative 2 equal the square root of 4? No. Negative 2 does not equal 2. So what does that tell me about the x equals 2 solution? Discard it. Only one of those we get to keep. One of them was extraneous. Okay? And once again, why didn't it work? Didn't work because it's what we call an extraneous solution, right? That's just one that's extra and doesn't work. Okay, false solution. Okay, gotta check your solutions. Make sense? It's in the bag. You got it. That's it.
I think the walls are there.
World is ending.